Okay, we're going to talk about quadratic functions and particularly talk about complex numbers. The complex numbers is when you have square root of -1 on your calculation. When you get square root of -1, remember we said earlier that if you get a negative number under the radical, we will not have any real solution for it. So we wanted to always the number under radical be equal to positive. So if you do have a -1 under the radical, from now on, we're going to call that I. So if we get the -1, we're going to replace that with I, and we call that a complex number. So I square, this is something that you want to perhaps put it on your summary sheet. It's going to show up quite a bit in your calculations later. I square would be equal to -1. The reason is if I have square root of A times square root of A, that is the same as A, right? Because this would be square root of A squared, and that would be equal to A. So if I have I squared would be square root of -1 times square root of -1. So your A is -1 really. So I squared is equal to -1. Maybe somebody asked me why this is not equal to +1, because if I square root of A times square root of B, remember we called that equal to square root of AB? You remember this property we learned? We said square root of A times square root of B is equal to square root of AB, right? But we cannot use that on here because this property was only good when both A and B were positive. It's not going to work when A is negative. So when A is negative, you're going to use this other property here. That square root of A times square root of A is equal to A. So your A is -1, so I squared is equal to -1. So far, the two things you want to perhaps write in your summary sheet, that everywhere you see square root of -1 somewhere, you're going to replace it with I. Everywhere you see I square, we know that's equal to square root of -1 times square root of -1, which is equal to -1. So if you can remember these two, we can speed up a lot of calculations here. So in this case, the number of the form A plus BI, this is called the standard form. So if somebody asks you to write the answer in the standard form, they're referring to this form here, A plus BI, where A is a real part of your number, and your B is, this coefficient would be imaginary part or complex part of that. So if I have a number -8, if I want to write this in the form of standard form, doesn't look like I have any I in there. So we only have real numbers there. So this would be -8 plus 0I. The reason we don't have any complex number there because its coefficient is 0. Like 0 is also a real number. If I want to write 0 in terms of the standard form, I would write as 0 plus 0I. However, 3I is a purely imaginary number. So if I want to write in standard form, I don't have any real part of that, would be 0 plus 3I. The next example, -I plus 2. If I want to write this in standard form, I'm going to write the real part first, which is 2. 2 would be a real part, and -I, -1I would be my imaginary part. And finally, if I have 8 plus I radical 3, 8 would be my real part, and the rest would be the imaginary part. So these are correspond to imaginary part. So let's take a look at this example. We want to express square root of -A. So in this example, you're going to separate these. You have part of this would be -1 times A. So if I separate that, that's really square root of -1 times square root of A. So remember I said everywhere we see square root of -1, we're going to replace that with I. So this really is I radical A. So if A is greater than 0, then that would be the case. Now you want to write square root of -A as I radical A. So you want to write this one here in terms of is imaginary number. So we can separate this. This would be minus 1 times radical 16. This would be minus 1 times radical 75. If you separate that, the minus 1, square root of minus 1 would be equal to I, and then we'll just simply deal with the real part, which is a square root of 18, which would be simply 4. Square root of 18, square root of 16 is equal to 4, so that would be 4 times I, so 4I. That's how you can separate them. Now, the next example here, we're going to separate minus 1 from 75. So this would be my square root of minus 1 times square root of 75. This portion, we said we're going to replace it with I. So it would be I times square root of 75. And 75, we're going to write it as part of 75 is perfectly squared, right? It would be 25 times 3. So that would be square root of 25 would be 5. And then that would be square root of 3. So it would be 5I square root of 3. You can write this in any order you want. You can write 5 radical 3 times I, and so on. Okay, so you can always use your calculator to evaluate this as well. So for those of you with your calculator, you can try this now. If you have any problem getting into these functions on your calculator, let me know. YouTube would be a good place to check your calculator for any of these functions. All right, let's take a look at this. Find, multiply or divide as indicated. So here we have the complex number to multiply. The first one, A, is square root of minus 7, square root of minus 7. So what we're going to do is we're going to subtract those i's from these. So this one would be minus 1 times radical 7, right? This would be minus 1 times radical 7. So I can replace this with I radical 7, right? That would be I radical 7. Because remember, this is minus 1 times square root of minus 1 times square root of 7. This would be I. That would be square root of 7. So it would be I radical 7. The next one would be I radical 7. Now, what's I times I? That would be I squared. Recall I said everywhere you see I squared, you want to replace it with minus 1. So we're going to remember that. It's going to show up quite a bit in your calculation in this section. So make sure you remember that. So here I get I squared. I'm going to replace that with negative 1. And then square root of 7 squared would be simply 7. So this whole thing would be negative 7. And that should make sense, right? Because we said radical A times radical A is equal to A. Your A is negative 7. You could use that, the fact that radical A times radical A is equal to A, and your A is negative 7. All right, next one. I'm going to separate these. This would be the square root of minus 1 times square root of 6. This would be the square root of minus 1 times square root of 10. This would be I. That would be I. So that would be I radical 6 times I radical 10. So I times I would be I squared. I'm going to replace it with minus 1. Radical 6 times 10 would be radical 60. So remember, part of 60 is perfectly square, which is 4. 4 times 15. So radical 4 would be 2, and then radical 15 stays on the radical. So this whole thing would be equal to minus 2 radical 15. All right, multiplying and dividing. In this case, we have radical minus 20 over radical 2. Remember, we can separate these. The first one becomes I radical 20 over I radical 2. The I reduces to 1. So this would be radical 20 over 2. Remember, when these are reducible, when you have radical A over radical B, if A and B are reducible, you make it into one radical to reduce. So that would be radical 20 over 2, which is equal to radical 10. The next one, only the top is complex, so I'm going to bring the I out. Would be I radical 45 And then this is also looks like it's reducible. 48 and 24, I can write as one radical. 48 over 24 would be equal to simply 2, so it would be I radical 2. You can also use our calculator to evaluate all these. Just punch the number there and they give you approximate number there. We want to find each sum or difference. Adding complex number would be like adding polynomials. You just add like terms. You add the real numbers together and you add the imaginary numbers together. So in this case, if I remove the parentheses, 3 and minus 2 can be combined as a real part of that. 3 minus 2 is equal to 1. And then minus 4i and plus 6i can be combined to minus 4 plus 6i. So the real part would be 1. The complex or imaginary part would be negative 4 plus 6 would be 2i. So we're writing it as a standard form, 1 plus 2i. Similarly, you subtract these, you just distribute the minus, and you do the same thing. You add minus 9 and minus 3. So you could actually distribute this minus 1 here and write it as minus 9 plus 7i, minus 3 plus 15i, and then combine the real part, which is minus 9 and minus 3 right here. And then you combine plus 7i plus 15i, then add up to 22i. So the minus 12 plus 22i, I'm writing this in standard form. So adding and subtracting complex number is quite simple. Just add the real parts together and add the complex part together. Here it would be a combination of those. We can go ahead and distribute this minus and pretty much add all the real numbers together and all the complex numbers together and find the final result. For those of you watching this later at home, you could pause these session and try to calculate these and confirm these results, of course. And then, of course, we can use our calculator to evaluate all that using the graphing calculator. Multiplying complex numbers would be just like multiplying binomials or polynomials that we did before. In this case, we just multiply term by term. And then be careful every time you see I squared, you want to replace it with minus 1. So you multiply 5 times 7, 5 times minus 2i, and so on. And then, again, once you get into combining these, you add all the i's together. You're most likely going to see I squared somewhere in your calculation. You're going to replace it with minus 1. And then you combine the real parts together and write it in standard form. This would be another example. Now would be a good time to kind of pause the session, see if you can do this on your own and see what you get in this set. So for this example here, we can either multiply term by term. We can go 6 times 6, which is equal to 36. Multiply 6 times minus 5i. What do we get? 30i minus 30i. And then here we multiply the next one, 5 times 6 plus 30i. And the next one we get 5 times minus 5. That give you minus 25i squared. If I multiply term by term, that's what happens, right? But you notice that that would be 30i, thank you. So this 2 would add up to 0, right? So you would get 36 minus 25i squared. But if you recall, if I have a plus b times a minus b, the result would be equal to difference of square, a squared minus b squared. So you should really use that, the fact that we have difference of two binomial, the conjugate of each other. So that if I have 6 plus 5i times 6 minus 5i, this is really the first term square, which is 6 squared, minus the second term square, which is 5i squared. So you can see you get 36 here minus 25i squared. If I replace I squared with minus 1, then you can see you get 36 plus 25, you get 61. Now look what happens here carefully. I had a complex number, 6 plus 5i. After I multiply this binomial, which contains complex number in it, with its conjugate, the conjugate of 6 plus 5i with 6 minus 5i, every time you multiply binomial by its conjugate, the result would be a real number. You don't have any I in there anymore. You don't have any complex number in there. We're going to use this fact to rationalize expression later. So keep that in mind. So let's take a look at this one. 4 plus 3i squared. I can write this as 4 plus 3i times 4 plus 3i and multiply term by term. But better yet, I can write this as a plus b squared. Anybody remember how to expand this? That would be the a squared and b squared at the end. What would be the middle term? Anybody? A squared. Not ab squared, we're almost there. 2ab. 2ab, right? Why? Because this is really is a plus b times a plus b, right? When I multiply term by term, here you get a squared, which is right here. Here I get b squared, which is right here. But if you multiply the two closest term and two furthest term, you get ab. So how many ab I have? 2ab. ab plus ab give you 2ab. So make sure you remember that. So in this case, I can use this fact that the first term squared would be 4 squared. Last term squared would be 3i squared, and 2ab would be 2 times 4 times 3i. If I combine this, what do I get? 16. 2 times 4 times 3 would be 24i. This would be 9i squared, right? That would be 3 squared times I squared, which is 9i squared. What is I squared? Is minus 1. So this would be minus 9. So now I can combine like terms. 16 plus minus 9 would be 7. So if I write this in standard form, it would be 7 plus 24i. Graphing calculator can also help you to evaluate these. You just enter the numbers, and as you can see, you can see the solutions like you did by hand. Power of I. So I to the power of 1 is equal to I. I to the power of 2, we said, is equal to minus 1. So I to the power of 2 is equal to minus 1. I'm not sure how this funny symbol arrived here. I'm going to erase it. I squared is equal to minus 1. So this would be, observe the following. Okay, this O and I got to get mixed together on the PowerPoint. I see what happened. We observe the following pattern. I squared is equal to I. I squared is equal to minus 1. We just said that. We're going to remember that. Now, I to the power of 3 would be I squared times I, right? Because you're adding the exponents. So we know that I squared is equal to minus 1. So I to the power of 3 is equal to minus I. Do we have to memorize that one too? Not really, because we can easily arrive to this by going through this calculation. I to the power of 4 is the one that you may want to memorize, because we're going to use that to simplify a lot of these I to the power of higher power. So I to the power of 4 is really I squared times I squared. I squared is minus 1. Minus 1 times minus 1 is equal to plus 1. So another thing that you want to maybe remember is I to the power of 4 is equal to plus 1. Okay, if you move on to I to the power of 5, I to the power of 5 is I to the power of 4 times I to the power of 4 is 1. and then would be I. So as you can see, as I simplify these, I to the power of nth power, you would get either plus or minus I, or plus or minus 1. So when they say simplify I to the power of nth power, they expect you to write either is equal to plus 1 or minus 1, or plus I or minus I. That's what you need to do. So any large power of I is found by writing the power as a product of two powers of I, one exponent and multiply of 4, and then simplify. What's that mean? Why 4? Why I to the power of 4? Anybody? Because remember I said I to the power of 4 is equal to 1. So we're going to use this I to the power of 4 to reduce or simplify the I to the power of higher power. So let's take a look at these examples here. If I want to write what I to the power of 13, or I to the power of 56, and I to the power of minus 3 is, what we do is, the first one, we have I to the power of 13. Okay, let's see how we come up with all this calculation here. What you need to do is you need to take 13 and divide 4 into that. Can somebody tell me why 4 again? Why I'm dividing into 4? Because I to the power of 4 is equal to 1. Very good. We do that. We use the fact that I to the power of 4 is equal to 1. If I divide this exponent 13 into 4, then I would know how many I to the power of 4 I have within that, so I can reduce that to 1. That's what we divide by 4. So if you divide it by 4, what do we get here? 3. 3 times 4 is equal to 12. What's the remainder? 1. The remainder is 1. So when the remainder is 1, it means I to the power of 13 then, I to the power of 13 is the same as I to the power of 4, then raised to the power of 3 times I to the power of the remainder 1. Remember, 3 times 4 plus 1 is 13. 3 times 4 plus 1 is equal to 13. So this portion, I to the power of 1, we know is 1, so it doesn't matter how many that I raise it to power of any number here, it's still going to be 1. So this whole thing would be equal to 1. So it looks like that you end up getting I to the power of the remainder always. So when you divide 4 into that number, you really care about the remainder then, right? Because the answer would be I to the power of the remainder. If the remainder would be 1, the whole thing would be equal to I to the power 1. So therefore, this whole thing is going to be 1. The reason we have I to the power 1 or I, because when I divide 4 into 13, I get a remainder of 1. Okay, similarly, if I want to know I to the power 56, if I divide 4 into 56, see what's going to happen? I would get what? 14, right? What is 14 times 4? What's that? 56. What's the remainder? 0. Remainder is 0. 0 is 0. It's not nothing. Okay? So 0 is remainder. So we know that this would be I to the power 4 to the power 14. That's it. So the remainder is 0. So it means the whole thing would be equal to I to the power of 0, really. Right? Which is 1. Anything to the power of 0 is equal to 1. So if the remainder is 0, you can remember that the whole thing would be always equal to 1. If the remainder is 1, the whole thing would be equal to I, and so on. So what's going to happen if the remainder is 2? The whole thing would be equal to I to the power of 2, which is negative 1. The whole thing would be, remember, we're going to get it into either plus 1 or minus 1, or plus I or negative I. Okay? So, and you pretty much look at the remainder. So if the remainder is 1, the whole thing would be equal to I to the power of 1. If the remainder is 0, the whole thing would be I to the power of 0, which is 1. If the remainder is 2, that would be I to the power of 2, which is negative 1. What if the remainder is 3? The whole thing would be equal to I to the power of 3. What is I to the power of 3? It would be I squared times I squared is negative 1, so the whole thing would be equal to negative I. Remember, we all either get plus or minus I or plus or minus 1. All right, next example here, we have I to the power of minus 3. So we need to eliminate that negative, right? But remember the property we had, a to the power of minus n is equal to 1 over a to the power of plus n. Do you remember that? That's how you can change it to positive. So in this case, you could change this to, if you wanted to eliminate that negative, you could write this as 1 over I to the power of plus 3, like that, if you don't want to deal with the negative. And then I to the power of 3, we already know what I to the power of 3 is, right? Because I to the power of 3 is equal to I squared times I, right? What's I squared? Negative 1. So this whole thing would be equal to 1 over negative I, right? Negative I. Can I have I at the bottom of the fraction? No. How do you eliminate that? Multiply by I. You multiply top, bottom by I. That's just another way to do this. So that the top would be I, the bottom would be minus I squared. So this whole thing would be equal to I over minus I squared is minus 1. You get 1 over 1. I over 1, which is I. Same answer we got right here. Here's a different approach. What they do is they're changing I to the power of minus 3 to minus 4 plus 1. And then this portion here would be a minus 4 to the power of minus I. It's just totally different approach. I really like this approach here. It's more cleaner because we know I to the power of 3 is equal to I squared times I. And then I squared is equal to minus 1. And then we can rationalize that at the end. So either way would be fine. You get I for either of these cases. So and of course, we can use our calculator to evaluate all that. The complex conjugate of the complex number a plus bi is a minus bi. So we use this to rationalize expression later. So every time you see a plus bi, if I multiply by a minus bi, the product of that would be a squared minus b squared. So these squares would eliminate the I in our calculation. So if I want to simplify this, or let's say find the quotient, or sometimes they refer to as rationalize this, I need to multiply top and bottom of the fraction by a conjugate of 3 plus I. What is conjugate of 3 plus I? 3 minus I, right? You multiply top and bottom of the fraction by 3 minus I. So you see this difference of a square. This would be a squared, which is 9. B squared would be I squared. So you see how you get I squared is equal to negative 1. So bottom of the fraction, you get 9 minus 1, which is 9 plus 1, which is 10. So you notice that it's okay to have a I at the top of the fraction, not bottom of the fraction. So here we just simply multiply term by term and combine like terms. You get 20 minus 10i over 10. We could separate these if we write the standard notation. Write 20 over 10 minus 10 over 10i. So you can write it as 2 minus I. That would be the standard notation. All right, similarly, if I have 3 plus 2i over 5 minus I, you multiply 5 minus I with its conjugate, which is 5 plus I, and then we proceed the same way. A squared would be 25, B squared would be I squared. So you notice that at the bottom of the fraction, we replace I squared with negative 1, you would get, we get rid of the I or eliminate I at the bottom of the fraction. And then you can write it in standard form, similarly. Next one, 3 over I. See how, if I want to eliminate I, if you only have one I at the bottom fraction, you just multiply it by I. We did a similar problem like that earlier. You multiply top and bottom fraction by I. You could just multiply by I over I, or minus I over minus I, that's fine. You would get I squared here, and that's how you eliminate I at the bottom of the fraction. And we can easily, again, check all this result using our calculator.